So get the idea? You know, and this must be the power series, this must be the Taylor series centered at 0 of this guy. And if you don't believe it, take derivative 1 at a time. I'm not going to do that. Alright? Okay. Next one. Find the Taylor series centered at 0. Well, actually, centered at 0 of x squared sine x. And I will be very, very disappointed if next semester in Calculus 3, many of you have to take Calculus 3, and then you're asked to do this, and you start taking derivative 1 at a time. I'll be very disappointed. So, I mean, this 3 o'clock in the morning, you know what you are expected to do, and do whatever you have to do, and then this only take 1 extra second. Is that right? Why? Because x squared sine x, I know that there is a series that converges to sine x. Series centered at 0 less than that. Well, that's something that you have to memorize. Right? Right? And what do? Huh? Yeah, just distribute. Right? You know, x third power minus x fifth power, 3 factorial, plus x seventh power over factorial minus x 9th power over 7 factorial plus That's it. Could we practice again? Try to cast this into summation. What would you do? Be careful in all the details. N equal to 1 to infinity. And depends upon what you want to do here, then you design a counter differently. Right? So what would you like to do?
Let's just do 0 to infinity.
You want to do 0? Okay, if you do 0, be careful. 0, alternating, is that right? So negative 1 to the 0 to the nth power, that would do, right? That takes a sign, properly, right? And start alternating, start with 1, right? Positive, positive. And then x to the certain power, what power? If you go for n going from 0 to infinity, then what should I do here?
Is it 2n plus 1?
Nope, 2n plus 3. Right, that's why I say it depends upon what you want to do. Here, the counter has to be designed differently. Had I let n start with 1, right?
Then it would be 2n.
Then it will be 2n plus 1. But if I let n start with 0, then you have to write 2n plus 3 here. And then divided by what?
2n plus 3.
2n plus 1 factorial. See that? This is always 2 less than, you know? Right.
So the counter starts with 1, writing it as 2n plus 1, but either
Right.
is, both are acceptable forms.
Yeah, both are acceptable, but you have to be consistent.
Right.
Yeah. All right. So that's that. And then we haven't talked about something that will be mainly, you know, not all of you are engineering students, but engineering students have to know this. So find the Taylor series of this function, hyperbolic sine of x. Yeah. So what is hyperbolic sine of x? And at one point I'm gonna make a brief introduction to it. But for now, you just remember that this is e to the x minus e to the negative x divided by 2. Okay? So that's the definition. That's called hyperbolic sine. Hyperbolic sine function.
Call it sinh as well.
Yeah. Yeah. Actually, most of the time I'll simply write SH. Okay. If I want the Taylor series centered at 0, that is to say Maclaurin series, this shouldn't be hard, right? Why? Because hyperbolic sine x is, by definition, 1/2 e to the x minus e to the negative x. And let me put a big bracket here, brackets. 1/2 of two things involved in subtraction. Is that right? Okay. What is the first one? E to the x. E to the x, can you represent it as a power series in x? That's something that you have to immediately answer. Is that right? X squared over 2 factorial. X cubed over 3 factorial, and so on. That's e to the x. What is e to the negative x? If e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, then what is e to the negative x?
So with all the x's down factorials.
Yeah, you just replace x by negative x. Right? So what is that? 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial. Are you with me? I mean, this works for all x. Remember, this one works for all x. Right? And so whatever x stands for, negative x is a number. Alright? So supposedly plug it in, it should work. Everywhere you see x is replaced by negative x. Left and right. Right? And so this one becomes 1 minus x, start alternating, 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus dot dot dot. Is that right? Okay. Now look at what happened here. So I put it in vertical form here. This one is e to the x is here. That one is e to the minus x is that. Then I have to take this and subtract this from that. This minus that. Is that right? And then remember, when it comes to power series, it behaves like term by term. Very nice. When it comes to addition, subtraction, right? Derivative, integration, you can do it term by term. Addition, quite obvious, you do it term by term. Subtraction, do it term by term, order by order, right? So if you take, just like polynomials, so if you take this minus that, what happens? You see that these are alternating, otherwise the same. Is that right? So if you take it to subtraction, all the even power term, they cancel out. Right? Whereas the odd, you'll get double. Why? Because x minus negative x is double. Is that right? This is x third power over 3 factorial minus negative x third power 3 factorial. That essentially is 7x third power 3 factorial double. Is that right? But then what do? You add back. And so what's the net result of adding these two and then halve it?
Just got the odd
You get rid of all the even ones and you manage to retain the odd ones. Alright? So therefore you get what? X plus x third power over 3 factorial plus x fifth power over 5 factorial plus x seventh power over 7 factorial. All the odd power.
So you just get sine.
So
Yeah.
it's a sine
No,
of that.
no, 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 no.
Doesn't
Very
alter-
good question.
Doesn't alter.
Oh, yeah, it doesn't alternate. Uh-huh. Doesn't alternate. And you're wondering, are these two guys cousins of each other? Yeah? You know, sine on the one hand and hyperbolic sine on the other. They are indeed cousins. Alright, so I don't expect you have learned this, but you see, hyperbolic sine of x, that one, let me copy that. This one is in chapter, last semester we didn't cover that because, there's a lot of students who are not in engineering, so I didn't want to, in calculus 1, a lot of students, they only have to take calculus 1, so I didn't want to overburden them. So there's a section in chapter, what is that chapter? Chapter 4 of 5, right? I think it's chapter 4, and no, chapter 5. What's that? Hyperbolic. Oh, chapter 3 actually. Chapter 3, 257. Page 257. How many of you actually have that last semester in hyperbolic trig function? You have that. You have that. Several of you. And so it's all in that section back in chapter 3. At the end of that chapter, there's a section of hyperbolic functions, and the first one is this one. Okay, now go back to that. This one is not sine. See that sine x we learned earlier, recently, that this one is equal to x minus x third power over 3 factorial plus x fifth power over 5 factorial minus x seventh power 7 factorial. It's alternating. Our power term is alternating. This one resembles that, except that it doesn't alternate. So all plus, all adding. Okay? Now guess what? This one is this. Which means that this one is hyperbolic sine of Ix divided by I. Look at this. If you take this one, or you can do it the other way. You can do it the other way. This one, you can think of it as sine of x over I times I think. And so look at this. If you take this one and then everywhere the sine x, hyperbolic sine x is this. Is that right? Hyperbolic sine Ix will be equal to what? We just replace x by Ix. If you replace x by Ix everywhere, then you get this piece, right? And then you then divide out I, and then presumably you'll get this. So let's check. First one is x. Replace x by Ix. That's Ix. Divided by I, what do you get? X. Right. Second one. If you replace x by Ix to the third power, that's I to the third power, x to the third power. What is I to